That's better. Yeah.
Okay. I welcome you all for the week 5 live interactive session for the course Polymers Concepts, Properties, Uses and Sustainability. Let's get into the session. So you're able to see my screen, right?
Yes, yes.
Okay. Let's get on to the session. So as usual, we'll go through the brief recap of lectures of week 5. So week 5 lectures, it started with blends and composites, where the lecture 30 was on microstructure in polymers. It was on concepts. So where polymeric microstructures were discussed. So what are the key features, that determines the microstructures in case of, polymers. So for example, in amorphous and glassy polymers, the orientation plays a critical role. And then in case of semi-crystalline polymer, the crystals, the lamella, its distribution, that, and then the orientation, which plays critical role were discussed. Right. Similarly, in case of copolymers and blends, it is the domain size and the shape, right? And for composites, it's the distribution and orientation of the reinforcements, right? So these are all the critical parameters. And what is the phase separation for milk crystal? And in case of blend, you have the A rich and A lean phase. So what is the energy of crystallization or energy of mixing involved? And what are the regions of a polymer blend? And what is the nucleation and growth, right? Were discussed. And the Gibbs free energy for nucleation and growth. And what are the parameters for the processing and microstructure, right? There are certain cases where the flow induced or the flow actually decides the microstructure, right? And then in some cases there are field assisted, like electric field or a magnetic field, that assist in forming, the microstructure of the formation of microstructure of the polymers, right?
Yeah.
And then lecture 31 was on composites. So an introduction to the natural composite wood was given. So wood is a natural composite of cellulose and lignin. So there was a description on this natural composite. And then what are the other polymer composites present, right? And then what kind of reinforcement can be there, whether they can be a long continuous fibers, they can be long fibers, short fibers, whiskers, particles, right? These kind of composites can be formed. And what is the size of reinforcement and loading of the fiber, right? How the load is distributed between the fiber, the uh, fiber and the polymer matrix. And what is the relation of a reinforcement, the size of the reinforcement and the ease of processing. And what are the different applications, like for example, composites in aerospace was discussed in detail, right? And then epoxy and bismillamide composites were discussed, right?
Yeah.
uh, the next was on, I think there is some echo from your side. Maybe you can just mute yourself when I'm speaking, so that is. And then the remaining lectures were on physicochemical, mechanical, and electrical properties of polymers, where basically the physicochemical and the mechanical properties were discussed. So the lecture 32 was on stress strain response. So it was on properties. So the mechanical response of polymers, the stress strain curves were discussed, the uniaxial tension, right? And then static mechanical tests for how the response would look like for a brittle, ductile, and flexible polymer. And what is the modulus? The slope of the stress strain curve gives the modulus, right? Especially the elastic modulus, and the tensile strength and toughness. So these were all discussed in detail in lecture 32. And the lecture 33 was on additives. It was on uses. right? Different types of additives were discussed. For example, what are the additives used for polymerization? Say, for example, some initiator may be there, or sometimes you may even add an inhibitor, right, for processing, for flow, and for performance enhancement, uh, right, like improving the strength, or mechanical response. How, what kind of additives are added, and then some other additional properties. What are the stabilizers added? So, and then there was detailed discussion on plasticizers, flame retardants, stabilizers, especially the antioxidants and the UV stabilizers, right? What are the impacts of the additives on in environment? Because these are again small molecules and they are capable of diffusing in and out. So they'll definitely have an impact when they come in contact with air, water, or soil, right? So these were also discussed in the lecture 33. Lecture 34 was on blends and composites in terms of sustainability, or especially in terms of recycling. So what is a polymer product life cycle, and what are the possible recycling mechanism, whether it is a chemical recycling or mechanical recycling was discussed. And the heterogeneities in polymer products, which makes it very challenging for recycling, right? One of the classic example that was discussed was the packaging, right? Food packaging. Now, how many layers you would find, for example, your Lay's chips packaging, you will find it as a thin layer of packaging, but it has multiple layers in that. The primary packaging, where you have the prints to be properly coming out, and then there should be some barrier properties. So for that, there will be a different combination of materials, and then materials giving structural properties. So different layers. So this makes it very complicated when it comes to recycling, because it is not a single material, but it's a blend of different materials. But how can it be really looked into, like using it as a plastic mix or a blends? You can, since it is already a mix of different polymers, you can just reuse it by making it as a blend. But what are the challenges while making it as a blend, whether they are compatible, right? So these things were all discussed. And how can you blend these plastic waste or polymeric waste with biopolymers? So for example, with starch or PLA, were all discussed in the lecture. Next was on the cross-linking, right? What are the different, so physical and chemical cross-linking were discussed in detail. So what are the different types of cross-linking? What is the purpose of cross-linking, right? What are the types of cross-linking? So based on crosslinks, type of crosslinks, you have physical and chemical crosslinks. Based on functionality, you have different types. Based on polymeric backbone reactivity, based on stimulus, right? Some may get cross-linked by use of light, photo cross-linking, right? Some may get cross-linked in acidic or basic environment, so pH based cross-linking, right? Some may be based on temperature, upon heating or upon cooling they get cross-linked. And then covalent cross-link was discussed in detail. What are the examples of cross-linked systems? Like hydrogels, you have supramolecular systems, you have, right? So these were all discussed. And then cross-linking in biomacromolecules was discussed, especially there was a detailed discussion on how pectin crosslinks. This is one of the fundamental component or matrix component in plant cell wall. So how does it crosslink? So it crosslinks basically due to the presence of your COH group. But when this COH group is, what happens? It interacts with the calcium ions to form crosslinks. It forms egg box structure, egg box bundles they form. But when this COH, if the H is replaced by a methyl group, then the cross-linking is not through calcium. It is through a different mechanism. Right? These were all discussed in detail, and how collagen and actin probably cross-links. Right? These were all discussed in the physical and chemical cross-linking lecture. Right? Next, lecture 36. It was on mechanical properties. And what are the mechanical response? So different modes. What is the stretch ratio? Right? And what is the elasticity? Like linear and non-linear elasticity were discussed. In linear elasticity, it is the energy spring, and the secondary interactions play a primary role. Whereas in non-linear elasticity, it's more of the segmental mobility. like in case of rubber, elastomeric rubber, elastomers. So there it is an entropy spring. So entropy determines the level of elasticity, right? And then uniaxial stretching in rubber was discussed, and then nonlinear elasticity, simple models like Monet-Rivlin model and Neo-Kean model were discussed. And final lecture of the week, again it was on mechanical properties. So different mechanical responses was discussed. What are different type of testing? For example, static testing, where you do the testing for small deformation and large deformation, right? And then dynamics testing, where it comes into it becomes very critical in case of a viscoelastic material, where you have both the viscous property or liquid like property as well as a solid like behavior. And then what are the different advanced mechanics of polymers, like failure or fracture mechanics, fatigue, impact, and then what is the effect of temperature and strain rate, and then concept of coarse graining of macromolecular systems and temperature superpositions. These were all discussed in lecture 37. Right? Now,
Yes.
yeah. Now let's get on to the practice assignment questions. So match the additives to their respective functions. So this is a GATE 2021 questions. They've given some set of additives and some functions also. So they've given triolyl phosphate, triethoxyvinylsilane, azo-iso-butyronitrile, and 4-methyl-2,6-di-tertiary butyl phenol. So these are some of the chemicals they have mentioned, and some of the functions what are mentioned, additives they have mentioned, and some of the functions they have mentioned are coupling agent, antioxidant, plasticizer, and blowing agent. Now we have to match which of these additives have which of the properties. So let's try.
Okay, let me try. Let me try.
Yeah, yeah, definitely.
So, so for my understanding, because I'm recalling myself, azonitro butyronitrile. According to me, this is a blowing agent.
Okay,
And in the phenol is there butyl phenol. So phenolic is mainly for antioxidant,
okay,
and the silane is a coupling agent.
okay,
So A is plus size.
okay. So you're perfectly right. Yes, triolyl phosphate is a plasticizer and triethoxyvinylsilane is a coupling agent. So these silane groups basically they play a role as a coupling agent in coupling this inorganic and organic groups. They form a chemical
Yeah.
bond between two non-similar species to enhance the interfacial bonding between them. For example, between fibers or particles with the polymer matrix. And as you said, isobutyronitriol is a blowing agent. So they work basically based on they may release some gaseous moiety and this help in forming foams and all. Okay, and finally methyl 4-methyl 2,6 di-tertiary butyl alcohol, sorry, tertiary butyl phenol. As you said, because of the phenolic group, they play a role as an antioxidant. So the phenolic group, how it actually play a role as antioxidant is through either hydrogen atom transfer or through single electron transfer or chelation of transition metals. So these are some of the mechanism by which phenol they scavenge this free radicals and help in antioxidant property. Okay.
Yes. Yes.
Now let's go to next question. A unidirectional composite of epoxy and carbon fiber for 50% by volume is made. The elastic modulus of epoxy and carbon fiber are 3.5 gigapascal and 350 gigapascal respectively. The ratio of modulus of the composite to the matrix modulus is, what is the ratio of modulus of the composite to the matrix modulus? This is the question. So this is a GATE 2021 question. So how to go about this? So what are the informations you have and how can you arrive at the required answer?
Yes. I don't have the direct equation because I don't know. And here they are given the epoxy modulus they are given and carbon fiber modulus they are given,
Yes.
and there is only 50 percentage filling.
Okay. Yes.
Okay. So and it is unidirectional means it is in the single direction. Carbon fibers are well oriented in the single direction.
Yes. Yes.
So, so 50%, 50%. So, so it's a direct. I think I don't know the formula. Maybe it's direct by weight fraction divided by uh, modulus plus weight fraction divided by modulus. I don't know. The direct formula is
Okay.
maybe there.
Okay, let's see the solution. So they've given elastic modulus of epoxy, which is 3.5 gigapascal, and carbon fiber, it is 350 gigapascal. So volume percent of carbon fiber is given. So volume fraction of carbon fiber is 0.5. Similarly, if carbon fiber volume fraction is 50%, the remaining 50% is going to be your matrix, which is epoxy. So volume fraction of
Correct.
epoxy is 0.5. So they've asked what is the modulus of the composite to the modulus of the matrix. So matrix is nothing but your epoxy. So epoxy modulus is 3.5, we know. So composite modulus is, so it is the modulus of the matrix into volume fraction of the matrix plus modulus of the fiber into volume fraction of fiber. So we have all the terms, right? I think can you just mute, because when I speak there is a echo from your this one. Yeah. So it is a direct, substitution. So you have the volume fractions of each and the modulus of both. So if you just substitute and do the mathematics, you will get the modulus of the composite as 176.75 gigapascal. So we just need the ratio of composite to the matrix, which is 176.75 by 3.5. You will end up with a value of 50.5. It's actually not gigapascal. Right? It should not have unit, right? I made a mistake here, right?
Yes, yes, yes. Right. Absolutely right.
Yes,
It
it
should be
should not
cancelled.
have unit because it's the ratio of similar quantities. So just hold on a moment. It is getting saved. So it is 50.5 is the answer. Okay. Now next. Toughness in a polymer can be inferred from, can we infer the toughness from izod impact strength or depth of indentation or area under the stress strain curve or Charpy impact strength? This is again a GATE 2022 question. Very straightforward question. How can you determine the toughness of a polymer?
Wait, this one because it's a tensile property. So my answer is C, area under the stress strain curve. But the thing is
Yes.
that Izod, Charpy, and are related with the impact strength.
Yes.
Both are impact strength. And
Yes.
depth of indentation is something like HDT or Vikat. That is the depth of indentation.
Yeah, okay.
It related with the temperature. So it is
Okay.
nothing to do with this one.
Yeah. Okay.
So yeah.
Yeah, as you said, it is perfect. So the toughness, it is the area under the stress strain curve, and it gives the energy absorption before failure. And you can just look into the trust, how the toughness of a brittle, and then a ductile and a flexible polymer looks like. These are general observations, but there may be some differences also in the area under the curve. Okay, now let's see next. Barrier height to be crossed for nucleation is directly proportional to the cube of interfacial energy. Is this statement true or false? Or tell me that the barrier height to be crossed is directly proportional to interfacial energy. Is it directly proportional or is it inversely proportional? So is the statement true or false?
Even I don't understand it. This is they are talking about blends.
No, this is for nucleation.
Nucleation means this is which one? Cross-linking or crystallization or something? What?
Crystallization process, for example.
So crystallization. Oh, no idea. I think it is true.
Or even in case of blends also, to form some nuclei of certain domains. There it
Yeah,
comes
I don't
more
know.
as a your what to say mixing rule than your barrier height. So this is more you can say it in terms of crystallization, especially in. So as you said, it is true. So this comes preferably in your crystallization actually. Okay, so if you just look into energy change when your nucleus is formed, so this is the uh, driving force, right? This term is your resistive force. That is why you have the negative. So you're driving. So your interfacial energy, if you have more of an interfacial energy, then it is it has to cross that interfacial energy for the nuclei to grow, right? It has to cross that because there is a interfacial energy between the growing nuclei and the surrounding fluid. So obviously it has to cross that barrier, right? So it is directly proportional to the cube of the interfacial energy, and this is by this relationship. Okay.
Okay.
Yeah, because the more the interfacial energy, then the barrier height to really form a nuclei is higher, because it has to cross that particular height. The size should be, or the particle size should be that much that it is able to counteract this interfacial energy, and it forms a stable nuclei. Okay, let's go to next question. The major reason for amorphous nature of lignin is, what is the major reason for amorphous nature of lignin? This was discussed in the lecture actually.
Maybe cross-linking.
Because of cross-linking? Actually, it is because of the presence of aromatic groups. So this aromatic groups restricts crystallization. Obviously, you have the
100%. Yes.
bulky group and it restricts crystallization. That is the reason why
100%.
lignin is amorphous in nature. Okay,
Yes.
next.
100%. 100%.
The critical fiber length for load transfer is directly proportional to the matrix ultimate shear strength and inversely proportional to the fiber tensile strength, or is it directly proportional to fiber ultimate tensile strength and inversely proportional to the fiber diameter, or is it directly proportional to fiber diameter and inversely proportional to fiber tensile strength, or is it directly proportional to fiber diameter and inversely proportional to the matrix shear strength? So which of these is right? The critical fiber length. For load transfer to happen. You can just go through the options again and just have a thought of it. And if you're not able to, then I'll say the answer.
Uh, exactly. My answer is B.
B. Directly proportional to the uh, ultimate strength of the fiber and inversely proportional to fiber diameter, you're saying. Okay. Now let's see the answer. It is actually directly proportional to fiber diameter and inversely proportional to the matrix shear strength. It is also directly proportional to the fiber ultimate tensile strength. So this is the formula. So the critical fiber length for load transfer to happen is, it is diameter of the fiber multiplied by the your ultimate strength of the fiber divided by the ultimate shear strength of the matrix. Okay.
This is short fiber composite The question is from short fiber composite.
Yes, 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 yes,
Oh,
yes. Because it is here where the fiber doesn't reach the maximum stress actually, because of the length being smaller. So at least for the load transfer to happen, so the critical fiber length should be of this function, so that the load transfer happens and you make use of the reinforcement properly. Okay.
but here it is. They're telling directly proportional to fiber diameter, means if the diameter is increasing, the load withstanding property is increasing.
Yes.
Uh, so why why we are
No, if the
thinking about
diameter
going?
is increasing, your critical length required increases. That is what they say. This is the
So it
critical
should be
length of it.
diameter and the length is also okay.
Okay, so if the
Uh,
diameter is increasing, the length should increase correspondingly. Then only, the load transfer will happen efficiently. That is what.
okay. The question is critical fiber
Fiber
length.
length.
Okay,
It is not of
okay,
the strength. Yeah.
No, I thought it about strength. This is
Okay,
the
okay,
problem.
okay.
Okay.
Yeah, I understood. Okay, now let's proceed with the next question. Flexible materials like rubber are characterized by yielding or very large deformation as high as 800%, or failure at low strains, or both A and C. What is the key characteristic feature? This was discussed in stress strain curves of brittle, flexible, and ductile materials.
No, obviously B is the answer, but yielding. Um, Yield. Yeah, rubber material will yield. Yes, both A and B. No. Only B is correct.
It's actually B, because yielding is
Yeah,
the nature of plastic,
correct.
conversion, right?
If they
Plasticity.
give A and B, I will be have more doubt.
Okay. It is actually C, very large deformation as high as 800%. You can stretch
Yes.
the material to as high as 800 percent. Okay. Next. Secondary interactions are strong with instantaneous initiation and propagation of crack in case of ductile polymers. So is it true or false? So when you have secondary interactions that are strong, then the initiation and propagation of crack happens in case of ductile materials. Is it true or false?
False.
Okay. So where does it happen?
In the starting itself.
I mean, to what kind of material it happens, or what kind of interaction it happens? The crack propagation is instantaneous. It actually, as you said, it is false. This happens mostly in your brittle materials. So secondary interactions are strong with instantaneous initiation and propagation of crack in case of brittle polymers. So in case of brittle polymers, only because of this secondary interactions being very strong, they tend to form cracks, instantaneously. Whereas
Okay.
yielding with orientation of macromolecules or crystals, or with large deformation depending on plasticity and eventual failures. This is what is the behavior for a ductile polymers. And when you have flexible polymers, you have weak secondary interaction. Stretching of segments happens to large deformation, and then there is recovery also on removal of load, and then the final stage is the eventual failure. Okay, let's proceed to next.
So what we are talking about creep here?
This is not really into your creep. This is just based on your instantaneous, time independent stress strain relationships.
For example, when cracking is happening here, so it's like environmental stress cracking or something.
It is just because of the secondary interactions, because in case of your brittle polymers, your secondary interactions are very higher. So when you tend to deform the material, this initially, instantaneously start to form cracks. That is why you see the failure very fast. If you just look into this, sorry, yeah, if you just look into this graph, the strain at failure is very, very small, right? Because the crack starts propagating.
Okay, now I got it, because we are talking about a tensile property here.
Yes, yes.
Okay, okay. Mm.
It's you do not really get into, yeah, yeah. It's more of your tensile properties. Sorry. Okay. Next question is, limiting oxygen index or critical oxygen index is given by the maximum volume percent of oxygen concentration in the mixture of nitrogen needed to support combustion of polymer, or is it the maximum concentration of pure oxygen needed to support combustion of polymer, or is it minimum concentration of pure oxygen needed to support combustion of polymers, or is it minimum volume percent of oxygen concentration in the mixture of nitrogen needed to support combustion of polymer? This was discussed when there was a discussion on flame retardants.
According to my understanding, it is the answer is C.
Is it okay? The minimum concentration of pure oxygen needed, you're saying. Okay,
Yeah.
so let's see the answer. It is actually D. It is the minimum volume percent of oxygen concentration in mixture of nitrogen needed to support combustion. It is not pure oxygen requirement. It is in the mixture.
So they are talking about the air itself, no?
Yes, yes, yes. So when it is in air, what is the minimum volume percent of oxygen
Yeah,
required?
yeah. So they are talking about air. Yeah.
Yes, yes. If lambda is a material time scale, what is 1 by strain rate?
What? I don't understand anything.
So you have in, okay, let me get into the answer. It is actually your experimental time scale. So this comes, when you're, talking of relaxation and understanding the polymeric behavior. Obviously, when you're doing some, mechanical testing, or even some, understanding the electrical behavior or any kind of a behavior, there is a material time scale where the material starts responding. You could see changes in the material response because of the material time scale or material relaxation, whereas there will be a certain time scale where you do the experiment, you actually do the testing. So this is where your Deborah number and Weisenberg number and all come into concepts. They are basically the ratios of these. uh, I think hope you are able to remember. The further explanation on Deborah and Weisenberg's numbers and all, which will be coming in the following lectures.
Okay, I look into the subject. Okay, no problem.
Yes. Next question. Which of the following statements are true with respect to cross-linking? So, cross-linking induces dominant viscous behavior, cross-linking induces dominant elastic behavior, or it makes the molar mass infinite, or it helps in easy recyclability. Which of the following are true with respect to cross-linking?
Yeah, I'll go with the answer B, because D is absolutely wrong. It is not easy to recyclable, and make molar mass infinite. Yeah, molar mass is infinite also, because cross-linking gives much higher molecular mass. So that is absolutely infinite. That's also correct. Induce elastic behavior means, if you are cross-linking, we will have only the elastic behavior, because it will break after that.
Is
So,
it true?
so I confused with B and C.
Okay. Okay. Now let's see the answer. It is actually both B and C. It induces dominant elastic
Oh,
behavior.
yeah, correct.
The
I got
material
it.
doesn't become completely elastic. Still, you will have viscous nature, because cross-linking you cannot just think of only thermosets. Okay, cross-linking
Yeah,
means even a hydrogel or a gel. There is a cross-linking, right? In hydrogels also there
yeah,
is a cross-linking, right? But
yes,
still,
yes.
there is a viscous nature because of the the water present, right? And also no, it is not highly cross-linked. They are all weakly cross-linked systems. So obviously there is a viscous nature there. but it induces more of a elastic behavior. It induces more of a solid like behavior. And similarly,
Yes.
the molar mass becomes infinite because of the cross-linked system. The system is getting cross-linked, all molecules are getting cross-linked. What happens is that it becomes a single macromolecular unit with the cross-links. Okay. And as you said, recyclability is very very difficult, or it becomes difficult as you once you start cross-linking the system. Okay. Yeah. Next.
Okay.
Next question. The type of cross-linking in cellulose is it covalent bonding, or is it physical bonding by hydrophobic interactions, or is it supramolecular, or is it physical by hydrogen bonding?
This physical by hydrogen bonding. I
Yes.
just looked into the lecture.
Okay. Yes. Yes. It is. It is a physical cross-linking by hydrogen bonding. Though it is a physical cross-linking, no, it is very strong material, right? The interactions are very very strong. So we should not imagine that only covalent cross-linking will make a very strong cross-linking. Even physical bonding through this hydrogen bonding interaction can also make the cross-linking very efficient. So cellulose is the
Yeah,
classic
because
example of that.
yeah, what I understand is that in this biopolymers, when the hydrogen bonding is occurring, it is the pool of hydrogen bond, not as in means the area of hydrogen bond within because it is too high. That's why it is become more
Yes.
cross-linkable like.
Yes, yes. Because as you said, the number of hydrogen bonds, the hydrogen bonding interactions are very, very high in case of
High.
biomacromolecules. Yes,
Yes.
yes. Supramolecular polymers or polymers where monomers are attached by.
Attached by. I think both means physical and chemical cross-linking.
Is it both? It is actually through physical interaction. Your supramolecular systems are systems where your monomers are attached by physical interactions. And in fact, your polymer is formed by physical interactions. Where in other cases like cellulose and all, the polymeric backbone is through covalent bonding, whereas the cross-linking is through physical interactions. Whereas in supramolecular systems, the backbone itself is made of physical interactions. Okay,
So if
and
so if backbone is made up of physical interaction means there is no polymer, no?
no, the physical interaction it makes it behave like a polymer. The physical interaction. See, for example, in case of cellulose, here you can straight away say that it is only physical hydrogen bonding, so it is not cross-linked. But still, that for cross-linking, the physical hydrogen bonding is so strong that you say it is a cross-linked system, right? The
Yeah,
similar
that's I agree. Yeah.
yeah, so the similar idea you have to bring into supramolecular systems, where the monomers are interacting through physical interactions and they form the chain of monomers through their physical interactions, they form polymers. Of course, you may not expect a similar property as a polypropylene or a covalently bonded polymer in
Yeah.
supramolecular. These are really new class of systems.
Yeah. So the supramolecular polymers, we can say it as polymers. This is my question because the molecular weight is depends on number of the linking together now, but there is no linking, only physical bonding.
No, this again, the physical bonding, it may have give that certain impact, right?
Impact will give, but no impact will give, but we cannot say it's like a polymer. I don't know because it is not a polymer. It
No,
is something else
no, you can call it as a supramolecular polymeric system, supramolecular systems.
because monomers are attached by means of physical bonds only, no chemical bonds.
Yes, but still, they behave as a single unit, right? Whatever of a covalently bonded polymeric systems, those fundamental theories applies to these also. But of course, the extent of property what you get may not be the same, and still they are all in research and not extensively into commercial applications. Okay.
Yeah, I got the idea. I got, yeah.
Yeah. Okay. Next question. The nonlinear elasticity is entropic in origin. Justify this statement.
You already told this one, non-elasticity entropic in nature already.
Yes.
Some slide before I saw this one. It's entropic in origin.
Yes, entropic in origin. Why is it so? That is a question.
I don't know. Because linear is depends on what is that? The linear. Linear elasticity, as you explained, is Hookean behavior, and this is no, Hookean spring behavior. This is entropic spring behavior. I don't know. You explained this one before.
Yeah, okay, okay. Let me say the answer. See, as you said, a linear elastic Hookean, it is actually energy spring. Your energy,
Yeah.
okay. Whereas here the nonlinear elasticity. So when the segments of crossing polymer get stretched, when they are deformed, there's a reduction or in the ways in which the segments adapts to different conformations. Okay, so when you stretch
Okay.
the polymer from a coil like straight, say for example a rubber polymer, rubbery material, when you stretch it, so uh, uh, your entropy, the number of configurations it can take gets reduced, right, as you stretch the polymer. Correct.
Mm-hmm.
So
Yeah,
the
yeah.
elasticity, so the entropy reduces, right? The number of conformational entropy, and this decides actually the elasticity. And once you release this, stretching, it comes back to the original state. So that is why your nonlinear elasticity is entropic in origin. Okay. Hope you are able to.
Yeah, I got it. I got it. But my question is that non-linear elasticity when it is related with entropy, but linear elasticity also have a some portion of this statement. Like there should be also a minor effect of this entropy also, no?
There will be effect, but which is the dominating effect? That is what is the question.
Okay.
So obviously you will have an entropic term as well as an enthalpic term or an
Okay.
internal
Okay.
energy term, but which plays the dominant role is what is deciding. Okay. Yeah. The next question is, nonlinear elastic response is due to dash for the following materials. So I'll just give you three set of materials. You have to say why there is a nonlinear elastic response in these. One is a semicrystalline polymer at high temperature. Two, polyethylene polypropylene blend. And then the third one is cross-linked rubber. Why there is a nonlinear elastic response? These three are completely three different systems. One is a semicrystalline system, another is a cross-linked a single polymer system, and the third one is a blend of two polymers. But all these three show nonlinear elastic response. Why is what is the reason behind nonlinear elastic response in each of these systems?
Hmm, this is completely. No idea because I'm not getting the idea.
Okay, okay. Let's see what is the answer. So, in case of your semicrystalline polymers, again, there is a crystalline domain, right? So, there is a crystalline domain and there is an amorphous domain also. So, again, your, I think if you can mute, no, I'll not get echo. Yeah. So, again, you have a crystalline domain and a, amorphous domain. And this amorphous domain, again, because of these crystalline domains, the stretching, once you stretch again your entropic between these crystalline domains, if you stretch, the amorphous domain expands. right? Again, your entropy, conformational entropy reduces. So this is one of the reason for semi-crystalline polymers for showing non-linear elastic behavior. Next is polyethylene and polypropylene blend. Again, here polypropylene, they are more of rigid, whereas polyethylene is more of flexible. So again, between the polypropylene domain, you will have polyethylene domain. Here again, if you stretch, for example, your conformational entropy reduces, and your elasticity brings in the nonlinear elasticity concept. And finally, in rubber, you have covalent cross linking, and I explained in the previous question itself that between the cross links, when the material is stretched, your conformational entropy reduces, and once you leave it, it comes back to the original state. And this is what is the origin for your nonlinear elasticity in case of cross linked rubber. Okay, let's go to next question. Change in internal energy in linear elasticity is what happens to the change in internal energy of the material in case of linear elasticity. You want to give a try?
Change in internal
What happens to your internal energy in case of linear elasticity?
increases.
It increases, or it gets stored, or it gets dissipated. What happens?
Okay, that is the idea. Okay, internal energy will elasticity it will store.
Yes, it gets stored as your strain energy. So, okay,
Yes.
simple questions. Okay, next question. Match the following: deformation till breaking, dynamic testing, large deformation, and damage in material due to repeated loading. So, what are the properties in each of these? So, elasticity for elastomeric polymers, fatigue, impact, viscoelasticity, fracture mechanics. So, you have to match. So, in each
Yeah,
case,
yeah. I'll try.
yeah,
Dynamic testing is viscoelasticity,
okay,
and damage of the material due to repeated loading is fatigue.
okay,
Mm, Elasticity of elasticity for elasticity for the elastic polymers is the large deformation,
okay,
and deformation till breaking is the fracture.
okay, okay.
I don't know from
Okay, now
it.
let's see what are the answers. Deformation till breaking is your fracture mechanics. Yes, as you said, perfect. Dynamic testing is for viscoelasticity. Large deformation is for elasticity of elastomeric materials, as you said, from the given option. And also for plasticity for ductile materials. Because plastic materials, the ductile materials also go through yielding, and still they can
Yeah.
withstand large deformation before they actually fail.
Yes.
Is there anyone joining?
Now. Yes.
Peshwar. Okay. And then the next is damage in material due to repeated loading is fatigue. Yes, perfect. And what is impact is? It is deformation and energy absorption at very fast rates of mechanical loading. Okay. Next question is, this is again a gate question. This was asked in gate 2020, 2017, and 2010. Okay. A glass fiber reinforced polypropylene composite is to be prepared with 20%, 20 volume percent of glass fiber. The density of glass fiber and polypropylene are 2540 kilogram per meter cube and 900 kilogram per meter cube respectively. The mass of glass fiber required to produce 1 kg of composite in kilogram is dash. What is the mass of glass fiber required to produce a composite having 20 volume percent of glass fiber? So what are the information given? And how to go about this question?
Okay, so the echo is coming. Here, density is given
Okay.
and volume fraction is given.
Okay.
So we will get a PP mass with the density and the volume.
Okay.
So,
Now,
so both mass factor we will get from the density and the volume, because 20% volume means 80% volume is for PP.
yes.
I don't know the calculation, but this mass we will get from here.
Yes.
Answer will be 0.413.
Okay. So you have calculated it also, someone.
It is calculated.
Visveshwar. Okay. 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 Now let's see how to solve it. As you said, you have volume, you have density. So obviously you can calculate mass.
Yes, sir. Yes, ma'am.
Yes. Yes. Okay. So how do you do that is, so you have the volume of glass fiber, which is 20%. So volume fraction is zero point 0.2. And then volume of polypropylene is 80%. Volume percent. So volume fraction is 0.8. So volume fraction of both together is 1. I think someone, yeah, yeah, Nishish, can you just mute yourself so that I won't get the echo? So the sum of volume fractions is 1. So now let's assume that there is a 1 meter cube of composite. So then volume of glass fiber is 0 0.2 and volume of polypropylene is 0.8 meter cube. You have the density also for glass fiber, which is 2540 kilogram per meter cube, and density for polypropylene, which is 900 kilogram per meter cube. And then mass of glass fiber, you can calculate. So density into volume, it is 2540 into 0 0.2, 508 kilogram. Mass of polypropylene, again density into volume, 900 into 0 0.8, 720 kilogram. So total mass will be 1228 kilogram. So from this you can calculate the mass fraction. So which is nothing but of glass fiber, which is 508 by 1228, which is 0.4137. So that means if 1 kg of composite is to be prepared, then you need 0.4137 kg of glass fiber. That's it. So this is a straightforward question. Okay. So that's all with the session. So you have any other doubts?
No. It's okay. Perfect.
Okay. Okay. I think Vishweshwar, I think you joined almost towards the end of the session. The session starts
Yeah.
at 4
Yes, ma'am.
4 p.m. Okay. Did you go through the lectures?
Yes, ma'am. I'm go to lecture, ma'am. After
Okay.
every day, ma'am.
Okay. So you have any other doubts?
No, ma'am. Solution. I have not practicing solution, ma'am.
Okay. Okay. So you have any doubts in the lecture content? Any concept you have any doubt?
No, ma'am.
Okay. No doubts. Okay. Fine. Were you able to solve the previous assignments? Hello, Vishweshwar?
Yes, ma'am.
You
Yes,
were
ma'am. Yes, ma'am.
you were able to solve it. Okay. You don't have any
Yes,
doubts
ma'am.
on that.
Yes, ma'am.
Okay.
I am not so solving, ma'am.
Okay.
I am not solving, ma'am.
Huh?
Yes.
I'm not.
I'm not solve previous assignments, sir.
Okay, you have not solved the previous assignments. Okay, okay, okay. Please go through the assignments just because the solutions are already put up for 1 to 4 assignments. So, but try to solve it, and then if you have doubts, go through the solution
Yes,
Okay.
ma'am.
In case you have doubts, you can just get back to us. You can also, write your questions in the forum. Okay.
Yes, ma'am.
Okay. So if you have any other doubts,
Uh, For me, nothing, because tomorrow who is going to take?
there is one more PMRF scholar. Uh, so
Okay,
his
because
name is
most of the case Sunday very difficult for me because I didn't attend any Sunday.
okay. No, it's actually not mandatory that you have to attend both the sessions. Okay.
Yeah, okay.
Uh, uh, you know the purpose of the session is that if you are able to attend, so that you will have some practice on the assignment questions, some practice assignment
Yeah,
questions,
I got
uh,
it. Yeah.
and if you have doubts, you can just get it clarified. Okay.
Yes. Yes. Okay. So okay, thank you very much
Yeah,
today.
thank you both of you. Have a
Okay,
nice
thank you.
weekend.
Yeah.